Could the waters of Lake Geneva help physicists to unravel the nature and origin of the most energetic particles bombarding our planet? At low energies, neutrinos are the most feebly interacting particles that we know of. To capture appreciable numbers of neutrinos for study, we are forced to produce incredibly intense and focused neutrino beams, fire those beams through massive detectors, and remain incredibly patient. Typically, neutrino beams are produced by smashing high-energy protons into a target to create charged particles called pions. Magnetic horns focus these pions into a directed beam. The pions then decay in flight into muons and neutrinos. Finally, massive shields absorb the muons, producing a neutrino beam. So it's clear that particle collisions are a prerequisite for producing intense neutrino beams. That points to a phenomenally intriguing possibility. The Large Hadron Collider is the world's largest and most powerful particle collider, and when protons smash together inside the LHC, copious numbers of pions and related hadrons, such as kaons, charm mesons, and B mesons, are produced along the beamline and fire out in opposite directions. As these hadrons decay, they produce highly intense, collimated beams of all three flavours of neutrino: electron, muon, and tau. These beams contain the most energetic neutrinos man is currently capable of producing. These elusive particles usually pass right through the LHC detectors without interacting and are simply lost to the environment, their presence being inferred only as missing energy in particle collisions. However, with intelligent detector design and patience, these elusive particles can be captured and studied in downstream subsidiary experiments. Phaser is a 1-ton neutrino experiment located in a service tunnel 480 meters downstream from the Atlas interaction point at the LHC, and exactly along the line of sight for high-energy neutrinos produced in Atlas collisions. Countless high-energy collider neutrinos stream through Phaser and other close-by line-of-sight experiments such as SND, and were first detected in 2023, allowing the interaction rates of tera-electron-volt energy scale electron and muon neutrinos to be measured for the first time. The success of experiments like Phaser and SND, and their ability to probe the properties of neutrinos in unique scenarios and energy regimes forward of the LHC detectors, has led to a desire for a dedicated forward physics facility at CERN. The Forward Physics Facility, or FPF, is a proposed underground cavern at CERN to be dug and located 627 meters downstream of the Atlas interaction point. It would house a suite of experiments: FLARE, Phaser V2, Phaser 2, and Formosa, designed to capture the intense flux of high-energy neutrinos and any other long-lived particles, including light dark matter and particles with tiny fractions of an electronic charge, during the running of the high luminosity Large Hadron Collider. This is something I love about particle physics: the innovation and creativity of particle physicists. The LHC program was never designed with the detection of accelerated neutrinos in mind, but with a little creativity and out-of-the-box thinking, the infrastructure and power of the Large Hadron Collider facilitates cutting-edge neutrino science that could not be contemplated anywhere else in the world. Energy Frontier Collider facilities are symbiotic infrastructure projects that facilitate more research programs than physicists could ever initially envisage, and offer unique and initially unexpected opportunities to chart energy and parameter spaces that no one has ever explored. A forward physics facility would allow us to continue to hunt for discrepancies from the standard model and enhance our physics reach far beyond the original plans for the LHC. They allow us to sail out from the harbour into a wider ocean of physics. Of course, as the state of science funding around the world cautions, all these extra physics explorations come with a price tag. Detectors designed to capture significant numbers of feebly interacting particles must be extremely large and contain tens of tons of target material. Such machines require space, and there is no such space for these experiments within the existing LHC tunnel system. To realise the forward physics facility, physicists therefore plan to dig a massive purpose-built cavern 100 metres below the surface. However, such a cavern would not come cheap. A significant fraction of the cost of particle colliders is in the boring of tunnels and underground caverns, just as those that endured the cancellation of the superconducting supercollider in the United States. As such, the forward physics facility, including its experiments, is expected to rack up a bill of roughly $100 million. But what if we didn't need to build such a cavern? What if there were a way to capture the particles barreling out along the axis of particle collisions without intense civil engineering and incurring the associated costs? It turns out that there is. The neutrinos and other potential long-lived particles spraying out from collisions in LHC experiments barrel through the rock surrounding the LHC, but they have to emerge from the Earth somewhere. We could place surface-based colliders at these emergence points and intercept these emerging particles without the need for any cavern excavation. Given that LHC collisions are so energetic and carry so much momentum in the forward direction, neutrino beams produced by LHC collisions are so flat to the LHC axis that they remain collimated for huge distances, spreading out to a beam radius of only about 10 meters at distances of 10 kilometers or more. This means that surface detectors could be constrained to acceptable sizes and kiloton mass ranges while still being able to capture the entirety of the widening beam. The initial cost of such service experiments would be higher than those planned for the forward physics facility for sure, but that additional cost would be more than offset by the total lack of need for civil engineering. In addition, the kilometers of rock between LHC collisions and the point where the line of sight of those collisions emerges from the surface would shield any surface detector from most of the particles flying out of the LHC collisions, including highly penetrating muons. This would ensure that only incredibly weakly interacting particles like neutrinos and potential dark matter candidates can reach surface detectors from the LHC. This would decrease the collider-based backgrounds. The Earth itself would provide an amazing, natural radiation shield. Of course, this all sounds fantastic in principle, but the points where the lines of sight from LHC particle collisions breach the Earth's surface were designed to minimize the radiation dose of Swiss and French citizens, not to optimize for the detection of neutrinos and other long-lived particles. So where are those emergence points, and how easy are they to leverage? Well, LHC physicists recently undertook a geographic and bathymetric study to answer just that question. They extrapolated the axis of LHC collisions, creating a beam line of sight, and using local geographical and bathymetric data, extrapolated that line of sight until it exited the Earth's crust in either direction. They found that the beams of particles produced in LHC collisions emerge anywhere from 9 to 183 kilometers from the collisions in the LHC, and that two of the closest and most promising emergence points are 9 kilometers east of the CMS detector and 26 kilometers northeast of the LHC-B detector. In both cases, the beam emerges deep under Lake Geneva. At these distances, the flux of neutrinos through a detector would likely be hundreds of times lower than that through an experiment sitting far closer to the LHC in a dedicated cavern at the forward physics facility. However, this decrease in flux can be negated by building a massive and cost-effective neutrino detector, and serendipitously, Lake Geneva could provide the calm waters for just such an experiment. Two of the main surface experiments hypothesized for the lake are massive water Cerenkov detectors, similar in nature to KM3 NET or Super Cameo Candé. Water Cherenkov detectors are vast tanks of ultra-pure water surrounded by rows of photomultiplier tubes that detect any light photons originating from that water. These detectors contain massive masses of water, some tens of thousands of tons, to maximize the probability of an elusive neutrino interacting with the water molecules in the tank. When neutrinos interact with atoms in water, they produce charged particles, electrons, muons, or tau leptons, corresponding to the flavour of the initially interacting neutrino. These charged particles barrel through the water faster than the speed of light in the water. When this occurs, they produce a cone of Cherenkov radiation, the radiation that produces the ghostly blue glow around operational nuclear reactors. This cone of radiation is projected onto and captured by a ring of photomultiplier tubes surrounding the water. The specific tubes that are hit help us to pin down the position and time of the original neutrino interaction in the water. The shape and nature of the Cherenkov ring can help to separate whether the light was produced by an energetic electron or muon, and hence determine whether an electron or muon neutrino originally interacted with the water. And the amount of Cherenkov light detected also gives an estimate of the energy of the charged particle producing the light, and hence upstream the energy of the initial incoming neutrino. The first water Cherenkov detector proposed for Lake Geneva is UNDINE, the Underwater Integrated Neutrino Experiment. UNDINE would be placed 26 kilometers northeast of LHC collisions in the LHC-B experiment, and would sit 50 meters below the surface of Lake Geneva. Here, it would be able to intercept neutrino beams as they exit the Earth for the first time through the bottom of the lake. Water Cherenkov detectors tend to be massive, rigid tanks of ultra-pure water, sited in huge caverns excavated under mountains to hide them away from cosmic radiation from space and ensure they operate in a quiet environment where they can detect neutrinos without huge radiation backgrounds. Hence, historically, massive water Cherenkov detectors like Super Kamiokande have required massive upfront capital. However, UNDINE seeks to mitigate much of this cost by taking advantage of the ingenious CHIPS detector concept. The CHIPS, or Cherenkov Detectors in Mine Pits Detector, is an R&D project designed to lower the cost of building large-scale water Cherenkov neutrino detectors. By submerging flexible modular detectors in naturally occurring bodies of water, such as abandoned mine pits or lakes, it aims to reduce construction costs of water Cherenkov detectors by an order of magnitude or more. Rather than excavating deep, expensive caverns and filling them with rigidly constructed tanks of water, the CHIPS detector encloses ultra-pure water in a light and watertight membrane and submerses it in a much larger, naturally occurring body of water. A 5 kiloton prototype has been built in a water-filled mine pit near Hoyt Lakes in Minnesota, United States. CHIPS is essentially a cheap, flexible, purified water balloon instrumented with photomultiplier tubes that can be easily submerged and held in place by the pressure of the surrounding water, negating the need for expensive support structures. It is essentially a portable and submersible mini Super Kamiokande. UNDINE would be composed of 5 cylindrical chip-style modules, approximately 12.5 meters in radius and 12.5 meters in height, providing a target water mass of roughly 30,000 tons. The experiment would be powered and controlled through cabling running to the shore. And the surrounding body of water provides an additional benefit. Instead of having to excavate a cavern under a mountain to block cosmic radiation, the tens of meters of water above the experiment block the majority of light and cosmic radiation from reaching the experiment, allowing it to operate with minimal backgrounds in a radiation-quiet environment. If highly penetrating muons happen to barrel through the water from the atmosphere and reach the detector, their arrival can be captured by externally facing photomultiplier tubes that capture the Cherenkov light produced by the muon as it dives through the water of the lake, and any interaction seen in the detector at that time can simply be thrown away. As such, Natural bodies of water provide phenomenal benefits both in terms of functionality and cost effectiveness for neutrino detection experiments. The ingenuity of the chip's concept, as well as the physical properties of Lake Geneva, mean that UNDINE could be deployed for less than $10 million, but still detect more than 100,000 neutrino interactions during the running of the high luminosity Large Hadron Collider. UNDINE is a proposal that seems to hold a lot of water. Another option for a water Cerenkov detector in Lake Geneva is the proposed FLOUNDER, or Forward LHC Observatory Underwater for Neutrinos and the Dark Sector experiment. FLOUNDER would be a 200 metre long, 3 by 3 metre cross-section detector with a target water mass of roughly 1,800 tonnes. It would be located 9 kilometres east of LHC collisions in the CMS detector and rest on the bottom of the lake at a depth of roughly 300 metres. Here, it would be able to intercept neutrino beams as they exit the Earth for the first time through the bottom of the lake. Placing this experiment would be more difficult, requiring the use of underwater submersibles. However, thanks to the collimation of the incoming beam, the experiment could still be placed in standard cylindrical housing structures, such as high-strength plastic pipes or non-rusting metal silos. It's worth noting that the collisions in the CMS detector at the LHC are more frequent than those in the LHCb experiment. LHCb actually focuses the LHC beams less than CMS to avoid being swamped with unnecessary proton-proton collisions. This means that 8 times more neutrinos would pass through FLOUNDER than UNDINE if they were at the same distance from LHC collisions. FLOUNDER is also only 9 kilometers from the CMS interactions, while UNDINE is 26 kilometers from those in LHCb. This increases the flux of neutrinos passing through FLOUNDER by an additional factor of 8 relative to UNDINE. However, on the flip side, the baseline design of FLOUNDER is 17 times less massive than UNDINE. In addition, the collision angles of collisions in the LHC is shifted between a slight angle up and a slight angle down during running periods. This shifts the position of the line of sight at FLOUNDER up and down by about 2¼ meters. As such, it turns out that FLOUNDER may only be able to intercept the neutrino beam coming from the CMS LHC collisions during the angle up configuration, and hence only half of the time. The upshot of all these competing considerations is that both FLOUNDER and UNDINE would be able to capture similar numbers of neutrino interactions, hundreds of thousands. Cost estimates for the FLOUNDER detector are not currently available, but from a physics perspective, it can dive just as deep as UNDINE. At this stage, it's worth noting that while water Cerenkov detectors can be deployed cost effectively, they suffer from several drawbacks. One of those drawbacks is that they cannot capture tau neutrino interactions. When a tau neutrino smashes into water, it produces a tau lepton. This tau lepton has an incredibly short lifetime of roughly 10 to the minus 13 seconds. Even at ultra-high collider energies, it travels only a few millimeters or microns before decaying into other particles. A water Cerenkov system simply does not have the sub-micron spatial resolution needed to see that tiny millimeter-long track, meaning it cannot separate the initial neutrino interaction vertex from the subsequent tau lepton decay vertex. To remedy this issue, an emulsion detector could be placed at FLOUNDER's position. An emulsion detector, like phaser, would consist of closely interleaved layers of heavy tungsten metal and emulsion plates. An incoming neutrino would interact in the dense tungsten plates and produce secondary charge particles that pass through the emulsion layers, leaving tracks of ionization. Tau neutrino interactions produce a short-lived tau lepton that would likely punch through one layer of emulsion before decaying into a lighter charged lepton such as an electron or muon and 2 invisible neutrinos. This charged lepton would leave a track in the next emulsion layer, but crucially at a different angle. This kinked structure of emulsion tracks would give away the short-lived tau lepton and allow tau neutrino interactions to be identified and distinguished from electron and muon neutrino interactions. The ability to capture tau neutrinos would be of great benefit, and an emulsion detector in Lake Geneva could substantially add to the global collection rate of tau neutrinos. A small prototype lake emulsion detector, or LED, could even be used as a small preliminary test unit to locate the exact beam location under Lake Geneva before larger experiments such as FLOUNDER or UNDINE are deployed. It could allow us to get our bearings in the murky depths. What I want you to realise is that it's possible to achieve neutrino interaction rates similar to those expected at the proposed forward physics facility at surface locations geographically separated from the underground structures of the LHC. Detectors at these surface locations have to be larger and more expensive for sure, but initial estimates suggest that those additional costs would be more than offset by the fact that they obviate the need to dig expensive, dedicated underground caverns close to the LHC detectors. In short, there are several ways to slake our thirst for forward physics. However, at this point you might ask, why is capturing and studying LHC-produced neutrinos so incredibly important? After all, other experiments capture solar, astrophysical, or accelerator-produced neutrinos. Why bother studying neutrinos produced at the LHC? There are many important and far-reaching physics motivations. Firstly, the measurement of high-energy neutrino cross-sections. Prior to the creation of the phaser experiment, the interaction rates of neutrinos with matter, or cross-section, had only been measured for moderate energy neutrinos created in moderate energy particle collisions, and for phenomenally high energy neutrinos originating from astrophysical sources. The LHC produces neutrinos at previously unexplored middle ground tera-electron volt energies. A surface neutrino detector would be able to capture millions of these interactions during the high luminosity LHC era, and allow physicists to precisely measure neutrino-nucleon interaction rates at energies bridging the gap between moderate energy accelerator experiments and deep space high energy neutrino observatories like IceCube. It would stress test the standard model in a previously largely unexplored regime. It would chart the open ocean of neutrino interactions with matter. A surface detector would also provide vital insights into forward hadronic production. The collisions at the LHC are so energetic and produce particles that are projected so flat to the beamline that LHC detectors like ATLAS and CMS struggle to capture and measure them. As such, there have been minimal measurements of forward hadronic production, the rate of production of particles such as pions, kaons and charmed mesons, very close to the beam axis of particle collisions. This means that theoretical models which predict the particles being produced at these trajectories are largely unconstrained. Given that different models make radically different predictions, which models of forward hadronic production should we trust? Surface neutrino experiments at the LHC may be able to answer this question. When forward boosted hadrons produced in LHC collisions decay, they produce the neutrino beams that would be detected by a surface-based neutrino experiment like UNDINE or FLOUNDER. As such, these neutrino beams are affected by and carry information about the composition of the hadrons that produce them, the hadrons that are produced in forward production, the hadrons that are produced in the forward direction during powerful LHC collisions. By detecting the flux and energy of surface-level collider neutrinos of various flavours, scientists can therefore back-calculate and map out the rates of forward hadron production inside the LHC. They can then compare these measurements with the predictions of various simulations and models to determine which of those models gets the physics right and which should be trusted going forwards. And that determination could have massive implications for complementary particle physics experiments and our studies of the universe around us. Our upper atmosphere is constantly being bombarded by high-energy particles from outer space, known as cosmic rays. Collisions between cosmic rays and atoms in the upper atmosphere produce scores of energetic hadrons tight along the trajectory of the original incoming cosmic ray, just as LHC collisions produce forward boosted hadrons. Astrophysics has long been plagued by an anomaly known as the cosmic ray muon puzzle, an unexpected 8 sigma excess of muons detected in high-energy atmospheric air showers relative to the numbers predicted by physics simulation models of cosmic ray interactions in the atmosphere based on the standard model. Studies suggest that the discrepancy may be a result of the mismodelling of strong QCD-based interactions at energies at and above the tera-electron-volt scale, the energy scale that LHC-produced neutrinos can reach. Physicists further hypothesize that the solution to the puzzle lies with so-called strangeness enhancement. Particle collisions might create an unexpected overproduction of strange quarks and hence hadrons like kaons in the forward direction relative to expectations. An overproduction of kaons would lead to a well-defined overproduction of neutrinos of various flavours. As such, by measuring the flavour composition of the LHC's forward neutrino beam at the surface, scientists can get a direct window into the exact underlying forward hadron production dynamics at the LHC. They can then pin down the hadrons that contribute most to the neutrino beam and help to solve a long-standing cosmic ray mystery. With this understanding in hand, and a finer-grained ability to model the interactions of cosmic rays with the upper atmosphere, physicists will be able to get a far better handle on the mass and particle composition of cosmic rays. This measurement will allow astrophysicists to distinguish between different hypotheses regarding the origins of the most energetic particles bombarding our planet. A greater understanding of forward hadronic production will also help us to understand exactly how cosmic rays form in the first instance, as particles are accelerated up to high speeds and smashed into one another in some of the most violent environments in our universe. After all, high-energy particle collisions don't only occur in man-made machines like the LHC. The universe is a far more powerful particle collider, and it is constantly sending us information about its nature, structure, and past in the form of energetic particles, cosmic rays. It is our duty as scientists to seek to understand and scrutinise those cosmic messengers, and to understand all the information about the depths of our universe that they encode. So, with all this in mind, should we still be looking to build the proposed forward physics facility, or should we be taking the dive with UNDINE and FLOUNDER? As we have seen, water Cerenkov detectors are capable of capturing similar numbers of neutrinos during the running of the high luminosity LHC as experiments based at the proposed forward physics facility. However, it's worth realising that while FLOUNDER and UNDINE may be attractive from a financial perspective, they are subject to limitations that experiments based in the forward physics facility are not. As we have seen, water Cerenkov detectors like FLOUNDER and UNDINE cannot identify tau neutrino interactions due to the low spatial resolution of their detection technologies. An emulsion detector like phaser far closer to the LHC interaction point can. In addition, there is no way to create a strong magnetic field across a cylinder of purified water in order to deflect the charged particles created by incoming neutrinos. As such, it's impossible to distinguish whether the particle produced by a neutrino interaction was a negative electron or a positive positron, a negative muon or a positive anti-muon. Upstream, that means that a water Cerenkov detector cannot distinguish whether the initial particle interacting in the water was a neutrino or an anti-neutrino. As such, water Cerenkov detectors can only measure the sum of the interaction rates of neutrinos and antineutrinos, and not their separate interaction rates. In contrast, an emulsion detector near the LHC interaction points can be bathed in a powerful magnetic field and allow the interactions of neutrinos and antineutrinos and their interaction rates to be separated. The bottom line is that while Geneva Lake-based detectors may be cost-effective and can reproduce much of the physics possible at the forward physics facility, they cannot recreate the entire physics program slated for that dedicated facility. As such, the route we ultimately choose to take will be a trade-off between physics reach, continuously squeezed science budgets, and wider political concerns. Do we want both surface detectors and a forward physics facility to maximise statistics and provide complementary results? Do we want to encourage research and development of neutrino detectors in existing bodies of water? Can we build massive experiments in a lake close to central Geneva without inflaming public fear of exposure to radiation, and while securing the efficient and unhindered operation of the detector? All of these matters need to be carefully discussed before a final decision can be reached. What is clear is that in a world and time where scientific funding is coming under increasing pressure and public scrutiny, it is wise to show flexibility and have potentially cheaper alternative experiments in your back pocket. It's important to be able to move with the tides. The innovation, resourcefulness, and out-of-the-box thinking of particle physics colleagues never ceases to amaze me. While the LHC may not have discovered the supersymmetric particles, microscopic black holes, and dark matter candidates we might have hoped for, there are still huge parameter spaces and massive far-reaching questions that can be explored and addressed at the high luminosity Large Hadron Collider. Whether Lake Geneva will play a part in that exploration is uncharted water. I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.